Hi, welcome to the Calculus 3 lecture series. We are in the unit Vector Calculus. This is our lecture number 5. And in this lecture, we're going to talk about a very interesting theory. We call it the fundamental theory of the line integrals. For the previous lecture number 4, we introduced what is the line integrals. We talk about the line integrals. So you can take the line integrals over the scalar field or over the vector fields, right? So how do we do it? We use the parametric form, change the parametric form, and then change all the integration to a one parameter t, and you integrate that. Okay, so today we're going to go over this topics here, the fundamental theory of the line integrals, and what is that, and why this is interesting and important. Okay, so let's go ahead, go to our lecture notes here. Okay, before we start to take a look here, all right, and so I'm going to take a look here. So in this videos, in this topic, lecture number 5, we're going to talk about several things here. So we already introduced what is a line integral from the previous, right? So the first things we're going to talk about is the fundamental theory of the line integrals. This certainly sounds very, very familiar, right? So then after we're going to see why this sounds very familiar. Then these are the first topics we're going to cover in these lectures. Then we're also going to talk about, we call this the independent of the path. So independent of the path for the line integrals. Wow, that's interesting, okay? And then the other things we're going to talk about a conservative field. Okay, then we want to take a look. So what is the relation of the conservative field and independent of the path? Are they have some relations here? And also we say conservative field. So from the previous lecture, we do the very basic definition. So we say if a field is a conservative, that means this field has to be the gradient vector field for some functions, the real value function f, right? That's what we say. If this vector field is the gradient vector of some functions, then we say this is a conservative field. And then the last thing here we want to do in these lectures, we're going to say, how do I test out the conservative field? Okay. So if you give me a vector field, how do I know this is a conservative? Of course, you can try to see, you'll be able to find these f functions or not, but how about if it's pretty complicated, it's not obvious. Now, how do I test for is this field is a conservative? Okay, so we will divide this lecture in 2 videos as well, and we don't want to be one video, it's too long here. So let's take a look at what is the fundamental theory of the line integrals here. All right, so this one here is certainly very familiar, right? So in the calculus 2, we talk about the fundamental theory of calculus, right? We talk about the fundamental theory of calculus. So what do we talk about? We said, okay, so if you integrate, right, AB, and if you integrate f of x dx here, if there existing like an antiderivative of the lowercase f, so this is f of x here, right? So That means the f prime x is going to equal to the f of x here. So if if the f of x, if existing antiderivative of f of x, then this ones here will show you what is that mean. That means if you integrate f of x from a to b, so that's what will tell you. This is f of b minus f of a here, right? That is what we learned in the fundamental theory of calculus in the calculus 2, right? So we said you find the antiderivative, and then you integrate it from a to b, it will just be equal to, you plug the endpoint f of b minus f of a here, right? So what is the theorem of the line integrals? It's the same ways here, okay? So let's take a look. So let's take a look here. This is my definitions of the fundamental theory of the line integrals here. So let's say if, okay, so if C is piecewise smooth curve, that means the C is a smooth curve, can be the combination of the several curves here. And then this curve is written by the R to the T. It's a parametric form like we learned before, right? And then we see the F is a differentiable function because we know, right? So this is just a very similar like in calculus 2. We know the del F is what? In the del F in the R2 is what? Is the partial for the X and the partial for what? Partial for y's here, right? So it's very similar like calculus 2, like you see here, this is the del F, and then you take the derivative along this curve, RT's here. So what going to be equal to? So the F's here, right? So this is kind of like the antiderivative of delta F, right? So then here, this will be F, then you put the endpoint. So what is the endpoint? Endpoint is where is this curve start. So this will be f of the b minus f of the a. That's right. So it's very similar like what we learned in the calculus 2, because the del f is the f of x, f of y. Those is the partial derivative. So it's kind of like then the f is very similar. So what is f here? Is very similar. I don't want to say is it. So like we talk about is the antiderivative, kind of a similar concept like we learned in the calculus 2, right? So it's kind of like a similar concept is antiderivative of del F here, all right? So that's why this is, we call it the fundamental theory of the line integrals here. Okay, so now let's take a look at the problem number 1 and just try to get familiar with it. Okay, so let's go ahead and get started here to see how do we do the problem number 1. Okay, so let's go ahead and start. So let's say if f of xy equal to x squared plus xy plus 2y, and C is any smooth curve from 0, 1 to 3, 0, I want to find what is the integration of the C del F and over this C passes here, right? Okay, because I know the f of xy is the similar like the antiderivative of this del F here, right? So by the fundamental theory of the line integral, so what I have here, that means when you integrate the del F will be F's, right? So that means what? It will be equal to what? It will be equal to whatever, right? So my F here, so the F here is the endpoint here is what? It's 3, 0, and the minus F of here, the 0, 1s here, right? So what is this one here? This is my RBs, right? This is my RBs. That means at the end, so this is my RB, so it's the end of this curve, right? This is what? This is my RAs, right? So it's the beginning of this curves here, right? So that's what we say. This is based on the fundamental theory of the line integral. Then you put a 3, 0 into your function. 3, so it will be 0, so it will be 9 minus 0, 1, so it's 9 minus 2, so it's equal to 7 here. Okay, so this one's here, he said, you know, look at this problem. They said C is any smooth curve from 0, 1 to 3 zeros here. Okay, so basically it's telling you, right? So like from 3, 0, so C can become here to here, right? So if this is my 0, 1, and this is what? This is 3 zeros, right? So this is my C. I can have another path. I can say, I can go this way, right? So this is another smooth curve. I can see one. It's also start from 0, 1 to 3, 0. So based on the fundamental theory of the line integrals here, so if this is a gradient vector, then doesn't matter, right? So it doesn't matter because based on the fundamental theory of line integral, I always use the end point minus the beginning point. So then in here, you know, if you have another path, this one, this is C2. So all these three paths, the line integral over this gradient vectors, then they will be the what? They will give you the same answers here, right? So it's a 7 because that's why it's based on this fundamental theory of the line integrals here. So that's what we call is independent of the path, right? So it doesn't matter. As long as you start with 0, end at 3, 0, then it always will give you the same answers here. Okay, so now let's take a look at this one here. Okay, second one, let's get very familiar with what is that means here. Okay, so F is a smooth curve defined by RT. Then we say, hey, RA equal to RB. Then I have a function, F is differentiable, and then the derivative of del F is continuous. So I want to find what is the C, the del F, and you know the del F, the integrator over this path is here. So I know because del F is the partial, so the F's here, right? So the F's here is kind of like we talk about is like the antiderivatives, right? So that means what is the answers here? By the fundamental theory of the line integral. So what I'm having here, I'm have RB here, and minus what? This is F of what? RA here, correct? And then because the RA and the RB and is equal, so what I have here, so I have zeros here, okay? So that means if you do in a closed loop, right? So this is if this is the C's here, right? So this is my starting point, right? Also is my end point. So I know if I have a closed curves here, right? Then my integration, the line integral over this field will be what? It will be zeros here, okay? Okay, so before we introduce the concept of the conservative independent of the past, and right now I'm going to introduce some very basic idea. The reason why it's just the definitions. And because the reason why we need to know this definition is because later when you say, oh, what is a conservative mean? What is the independent path means? So they will give you the formal mathematical definition. So they will say is in this closed regions and it's a simple curve. So what that means here, right? So okay, so let's take a look. We say, let's take a look at what is this one's here. It's kind of very intuitively true. So we say if it's a curve and it's defined by RTs, right? If this curve, I call it is closed. Well, that's just like we did before. That means your initial point is equal to what? Is equal to your starting point. Good. Okay, so now we say a curve is simple, right? That means your curve is not intersect. It doesn't have the, you know, it's not intersect itself. So that's why if you take a look at the graph here, so this graph here, right? So what type of the curve see here? This is simple, right? And then it does not touch itself, but this is not close, correct? because it's not the initial point, it's not equal to the beginning point. So these ones here, this curve go like this, go like a boom here. So the starting point equal to what? The beginning point. So this is close, but it's not what? It's not simple, right? The reason why it's not simple because they touch themselves here, okay? So the next things here, so we say, this one's here, right? So this one's here, the initial point, meet the starting point, meeting the end point. Then these curves here, they don't touch each other. So it's a close end simples here. All right. So because you will see those terminology later when we define what is independent of the path, what is conservative. So that's why you will know what is those definition means here. And then the other things here we want to talk about is, the domains here, a domain D, if it's open, okay, that means is every point is interior point. That means it does not have boundaries, right? So that means they don't have boundaries here. And then the next important kind of definition we say is connected. Okay, so what does that mean connected? That means if any 2 points can be connected by a path entirely inside the D, okay? And then the simply connected, that means every simple closed curve in D enclose only the points of the D, okay? So let's take a look here. So the first graph, that is it's simple, right? So the first graph we know is, this is open. Now let's take a look at this one. So for these domains here, it's a kind of intuitive truth, right? It's not connected, right? Because based on the definitions, you say if it's connected, then for any 2 points, you can find the path. So like here and here. So you find the path, and this path has to be all often it has to be inside the D. Obviously, this path is not, right? So because I have a piece of the region of here is outside the D here. Okay, so take a look at this one here. This graph here, this is what? This is connected. Why is connected? Because if you find any 2 points here, right? So you can find the path. So I say I can find the path, I can go find here. And this path is all inside this domains here. But, right, but this is not simple connected. Why? Because let's say if it's simple connected, right? So every simple closed curve enclose only the points of the D. So look at these areas here, right? So this is the simple closed curve, right? So this curve is a simple closed curve. But what is it close here? You include those points here, right? Those points is not in the D's here. So we said this is connected, but it is not simply connected. All right, like I said, we talk about those things here is just because later when we defined the different things, they will use this, and then because in the mathematical proof, we're going to use these assumptions here. So now let's take a look here. Okay, so what is this ones here? Okay, so this ones here, we say, okay, so for this ones here, we say, okay, this one from, the curve go boom, doom, 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 doom. Is this a simple? No, false. Why? How? Because it intersects itself, right? So you cannot intersect yourself. So is this a close? No, it's a false. That's right. Okay. All right. So now the next thing here we say is true or false. The following region is simply connected. Yes, this is true because it's connected here. If you have a point here, if a point here, right? So can I find the path? Oh, yes, I can find the path. Go dun, dun, dun here, right? I can find the path and, connect these 2 points. And also any closed path, right? So if I have a closed path here, then this closed path, all the point included in this closed path is in these regions, right? So I say, what is the here? This is truth here, okay? And then right now, okay, so let's take a look. Okay, so let's take a look at the next few very important definitions here. So this is the one we say is a path independent, right? So it's a path independent. So this definition is pretty straightforward. So we say a vector field F is independent of the path, right? So that means if you integrate over C1, you integrate over C2, you integrate over C3, they're all the same, right? Because based on the fundamental theory of the line integrals, if you can find F here, the field to be, if you can find this one to be the gradient field of some function, then like we did for the previous example number 2 here, right? So I think we did here, example number 1, right? So in here, then we say, hey, this is independent of the path. That means for any vector field, if it doesn't matter, then it's independent of the path here, right? So this definition is kind of the pretty straightforward. Okay, so then we know, okay, so we also defined the vector field. We say if the, if the vector field F is here, right? We say the F here, is you can find F is equal to some gradient field, then F is conservative, okay? So because from the example number 1, we say if the F is conservative, right? So if F is conservative, then F is independent of the path, okay? So, right? Okay, so now let's take a look here, right? So before we go any further, let's take a look. So then take a look at the number 5 here. So the number 5, they tell you that if F is, okay, if F is conservative and C is a smooth closed curve that starts and ends the points of A. Now, what happened to here? Let's make sure we understand this concept, right? So what happened to fill in the blank here, okay? So now we say here, okay? So we say, okay, so F in here, because they say if F is conservative here, all right? So we know if F is conservative, what's that mean? That means we know the F I can find some function, the gradient function of this one will be equal to my vector fields, right? So now I can say this one's here. Now I say, okay, this one's here will be the C, and I'm sorry here, C is on the bottom here, it's not a constant, all right? So here, that means I have the C, right? Then this is del F dot product dr. Right? Okay, so now the del F product dr, based on the fundamental theory of the line integral, what I have here, because this is the partial for some F, so I can say some continuous function F here, right? So for the RB minus F of what? RA. Good. All right. And because also we say this is what? This is a closed curve, right? It's start and end at the same point. So what is my final answers here? Is my final answer is zeros here, right? So I know if it is a conservative, then, it's independent of the path. And also this one demonstrates one very good things here. They tell you if it is a conservative, so if you have a closed path, then what happens here? Then if you have a closed paths, right? Then the line integration will be equal to what? Will be equal to 0, correct? Okay, so now let's take a look at the problem number 6 here, right? So the number 6, they tell you, they said, if the C1 and the C2 are two different paths from A to B in a region. Okay, so that means the integration here, C1 of this vector field equal to the C2 of this vector field. Can we conclude line integrals is independent of the paths here? Can we do that? The answer is what? No, we can't. Why? So because the independent of paths is not only just twos, right? So that means it requires the line integral. So the line integral along all the paths, indeed. All right, so that's why. So I cannot, if you give me two of them, I cannot say, hey, they are independent. No, I cannot do that, right? Because I need to prove all of them is there, right? Okay, and so now, okay, so we already said that if it's a conservative, then F is independent of the paths, okay? And so from the other ones, if you take a look here, so if F is a continuous vector field on an open, simple connected region, that's why I said, you know, you need to know what is those means, because, you know, in the proof of the theory, they're going to use this in the proof. So we say if this is independent of the path, okay, so if this is independent of the path, then we know the F here has to be conservative here. So that means you have to be able to find the function and where is the, you know, the gradient functions will be what? Will be these vectors here. So basically you combine these two. So we can do it if and only if, right? So we say F is conservative. Then we can do only, and you know, so we can do is independent of the path, right? So we said if the vector field is a conservative, then it's independent of the path, because if it's a conservative, you can find the del F, right? Then if it's independent of the path here, right? And if F is a continuous function, then F has to be conservative. So you can go both ways here. So the last things here, we want to see how do I test F is conservative or not. So this is the proof. I'm not going to prove here. If you are interested, you can go to see the proof. So that means if you can show rho P rho Y is equal to rho Q rho X, this is a very important test to see if your vector field is a conservative vector field or not, okay? All right, so now I'm going to do one more province here, and then we're going to stop here because then the next few provinces might take a little bit more time to do it. So we're going to save for the next videos here. Okay, so we say, hey, is f of xy, the 2x plus y, x plus ay, is the gradient for some function? What is this ask you? So if the capital F vector field is the gradient for some function, what's that mean? That means they ask you here, is the F is what? Conservative or not, right? That's basically they ask you, right? Because if you can find F is equal to the gradient of some functions, then F is conservative. That's what the definition. So basically they ask you, hey, is this function, is F is conservative or not? So based on my quick test, so I know this one, this is what? This is my PXY. And what is this one here? This is my what? QXY. So based on my conservative test just here, so I would say rho P rho y. All right, so rho p, rho y is what? Rho p, rho y is 1, correct? All right, good. Then rho q, rho x is here. Rho q, rho x is what? Is 1. They equal, right? So that means I know the rho p, rho y is equal to the rho q, rho x. So what I can conclude here, so I say F is conservative. And that means F is equal, you can find F is the gradient vector of some real value functions here. Okay, so then we have the remaining few problems, and we're going to wait for the next video. So the next video we're going to show you how do I find this function? Because if I can find this f of functions, right? So if I can find this f of functions, then I can apply the, so when you do the line integrals, and then you can just plug in the endpoint instead of change to the parametric form, those things, right? All right, so that's it. So let's stop here and for our first video. And so hope that you like this very good properties about the conservative and independent of the past, right? So it's very interesting. We learn something new, the fundamental theory of the line calculus, line integration. So it's kind of interesting. Okay, nice talk to you. And we're going to talk to you next video to finish these lectures here. Okay, bye.